I'm gonna do a short introduction and then I will pass you the floor, okay? So, do you
Perfect.
mind if we wait 2 more minutes? Just
No worries.
to have a little bit more people. So, good afternoon or good morning for those who join us on YouTube. We are about to start. Just a little while. Okay, I think we can start. Okay, so hello everyone. Welcome to another talk in our webinar series. Today we have the pleasure of having Anais Möller from the Swinburne University. Her research focuses on time domain astronomy and supernova cosmology. And she also a PI of Fink broker, one of the brokers selected by the Rubin Observatory to process the LSST alert streams. And she has kindly accepted our invitation to talk about this project. Before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link on our website or you can access it on our YouTube channel, LIneA MCTI. Anais, thank you very much for being with us today, and the floor is yours.
Thank you very much for the invitation. I'm very glad to share this with you. I'm gonna start sharing my screen. Actually, I'm sharing the screen and it's a mountain from South America. You may recognize it, it's a Fitzroy in the background. Today I'm gonna tell you a little bit about Fink. Fink is a broker we have designed for Rubin Observatory LSST. And I'm going to tell you how to enable time domain science using this data, which will be actually a quite big revolution in our way of seeing the transient sky. So I'm currently based in Australia, in the University of Swinburne, but I was recently also in France, where Fink actually started. So I'm going to tell you a little bit about that. So basically, the Rubin Observatory, it's an amazing telescope with a 7-meter equivalent telescope based in Chile. You can see on the top right, the dome as it was being constructed in Chile. It's a new observatory and it should be online at the end of 2023, maybe through COVID, a little bit later than that. Not only the telescope is very large, but it has the world's largest CCD camera with 3.2 by 10 to the 9 pixels. And the resolution of this camera is great with a resolution that you can resolve a golf ball 24 kilometers away. Now, the idea of LSST is to make a photometric survey of the sky. So doing imaging in 6 photometric bands covering from 300 to 1000 nanometers. So you have the usual GRI set, which are also the ones that were used in SDSS or DES, which I think LIneA people know pretty well. And then you have U and Y, which are actually extensions to that. Now, LSST will image the southern sky during a 10-year photometric survey. And each time an image is taken, it will map an area of the sky that is pretty big. So on the bottom left, you can actually see the field of view of the camera with a full moon to scale. So basically, we're increasing not only in depth, because we have a high resolution, very sensitive instrument, but we're also going wide. And we are having very wide field of view of the universe. Now, what will happen is that LSST will image the southern sky during 10 years. 90% of the time will be for a survey called the White Fast Deep. You can add as well if you want, which is basically scanning the southern hemisphere. And then you have mini surveys doing like the galactic plane, or also doing the deep drilling fields, which is something that we have been using a lot for supernova science. Now, what will happen is that Rubin will produce around 1,000 images per night, which is equivalent to 15 terabytes per night. And this is a huge amount of data we haven't seen before in photometric surveys. So it's a quite big revolution in the sense, how do we deal with these over 10 years? But most interestingly, for people that are doing time domain science or things, transient science, is that we will have around 10 million transient candidates per night detected by Rubin Observatory. Now, what are the data products that Rubin will produce? So Rubin is the observatory. LSST is a survey, so it's a legacy survey of space and time. So the data products will be the following. There will be every 30 seconds, there will be an image taken between 50 and 20 terabytes per night. And then from this image, there will be a difference image analysis, basically trying to find anything that is changing in the sky within 37 seconds. So this is actually public data. So the raw data is not public, but the prompt data product is actually public. And that's what I'm going to talk about in this talk. However, just for clarification, there will be other data products, especially if you are part from LST. There will be the prompt products database within 24 hours of observations, which will contain images, objects, and source catalogs from these different image analysis, but also the orbit catalogs for the solar system bodies, which is around 6 million, which is pretty large. Now, there will be, of course, data releases to the general public accessible via the LSST Science Platform and Data Access Centers. So there will be one every year and then one final at the end of the survey, the 10 years. Now, even if you don't have access to the proprietary data, which is advantageous for many science cases, you can still use the public data. And the idea is that the public data every 37 seconds will be streamed to the world. And I'm going to tell you a little bit how that will work. But what are the contexts of this stream? So for each alert, there will be the following things. There will be cutouts of the science image, the image that was observed, for example, last night, the image that was used for a template, which is an image that could be a month or a year old, and the difference images, the subtraction between the two of them. From that difference image, there will be some photometry taken out, which is basically a measurement of the luminosity in that color band passes. So you will get a light curve. Of course, either if you have detected today this object, it will be 1 point or 2 points, depending how many observations you have from that night. But you will have the history up to 1 year of that object. So in those coordinates. Now, maybe your science actually has very long-term variable objects. You will only receive this 1 year for that science. And additionally, you will get some features from the LSST project, which are yet to be defined. But there will be maybe some cross-matching with some catalogs or some very basic things out of the stream. Now, the big question here is how do you go for these 10 years of LSST from 10 million transients per night to something that we can actually use for science? And this is where my talk is going to be centered on. Basically, our idea was to take the 10 million transients per night from LSST and answer the question, how do you get promising candidates for your science? But also, we have so many instruments coming online in this decade that could be interesting to join science, have complementary observations. So how do you get that information all together and also coordinate follow-up to get more information from the interesting objects? And that's where Fink comes by. Fink is a broker designed specifically to do this. Now, the origins of Fink, and you have been hearing a lot about brokers from the seminar series, but the idea with the brokers was 2 years ago, in 2019, Rubin made a call for community brokers. And 14 letters of intent were sent, including one from Fink. And after a lot of work, there was a decision in August this year of selecting a handful of brokers to actually receive the full Rubin stream. So the idea is that these brokers will receive the whole 10 million transients per night produced by LSST. And this will happen over the 10 years of operations. Now, the brokers that you probably have already heard about are distributed around the world, with 3 of them in the US, 1 in Chile, and 3 originated in Europe. And now I am in Australia, so now we have also a little bit of the southern continent in Australia covered. And each of the brokers work independently, and there can be substream brokers, which is basically brokers that receive from these brokers, like us, they can receive a reduced stream of data, because 10 million is a lot of bandwidth. And probably in your science, because there's a lot of brokers, you won't need the 10 million. So the idea is that Fink can do that bridge as well for you. So if you have a broker that is specific for a science case, we can discuss about joining efforts. So how does Fink, what is Fink after all? First of all, it's not an acronym. A lot of people ask about this. It doesn't stand for anything. We just thought it was a great name. But aside from the naming, it's a community-driven effort. So it's open to anyone. We work with public data. Our code is public. We try to be as transparent as we can. So if you're interested, you can join us. We have been designed to work for Rubin LSST. So basically, this means that we design Fink to work with the big data volumes of LSST using cloud processing, distributed computing, etc. So if you're interested in those technologies, this is something that we put a big emphasis on. We want to tackle as many science cases as we can. So if there is a science case that the community is interested on, we want to hear from you and collaborate and build towards that science objective. And overall, from those 2019, where we were 3 only talking about Fink and trying to develop it, now we're a community of over 40 researchers around 7 countries, and we're growing. So the idea is that we can cover and we can touch the science of as many people as we want. Of course, engineering is a big part of Fink. So we also have a big team of engineers working with us, and they are making a lot of this possible. So we designed Fink for big data. We prototyped it, and we are now deployed. Actually, we're a working broker. Since 2020, we have an MOU with CTF. So we're processing the public stream from them. So actually, you can go right now at the finkportal.org and take a look at the data produced by CTF. We process it as if it were the Rubin data and make it available to the public. And we have our first white paper published in 2020, where you can find a little bit of the architecture of Fink and also preliminary science results. And within the authors, which you can see, it's a large collaboration even then, I highlight the contribution of 3 people. So Julien Peloton is our lead engineer, being the mastermind of all the processing of Fink. And Emily Ishida and I were the leads of the science and machine learning development. But of course, this is a community project, and a lot of the people in this author list have contributed to make Fink what it is right now. Now, we receive operational funding from the French Science Center to deploy in a supercomputing center there. What's interesting from deploying in that science center is that it's where half of the data of LSST will be processed and kept. So if you have proprietary data for LSST, we're hoping to join the public alerts and the proprietary data so you can do time domain science using that bridge. But that's something still to be done. Now, how does a broker work? So if you have never heard the name broker or what do we do, you may ask, how do you go from those 10 million transients per night to do some type of science? So Fink in a nutshell is basically this. We receive the alerts, we make some quality cuts, let's put it that way. These can be, for example, real bogus cuts. If you have ever worked with difference image analysis, you will know that there are a lot of artifacts generated by the difference imaging. So you have a detection which is really a problem with this abstraction, a problem with saturated stars, sometimes diffraction patterns, etc. So we don't want to say that that's a real transient in the sky. So the first thing is that we do quality cuts. And then all the alerts that pass those quality cuts, we actually make cross matches. What does that mean? We basically take the coordinates of this object and we try to see if there is a catalog like CDS SIMBAT that you may know from that has an object in that position or close by. But you can also do cross match with things that are a little bit more dynamic, like VOE events or GCN notices. For example, when you find a gravitational wave in LIGO Virgo, you produce an alert saying, look, there is something interesting in this region of the sky, and we can actually cross match with that. And we can also do with dynamic catalogs. Then what we do with these alerts, there is no selection here, it's just adding value to the alert, is that we produce what we call Fink features, which is basically computing things like rates, like magnitude increase rates or color if you have it. So that gives you an idea, a little bit of a quantitative way of selecting transients. And we have a big part of machine learning classification in our broker. Why? Because machine learning has proven to be great in classifying objects using only photometry and even partial photometry. And also because it's very scalable, it's very fast to actually get these classifications quickly. Now, what happens then is that with all those added values, even from Fink and also from the original alert, you can do some customizable filtering depending on the science case, and you can have a reduced stream. So basically you can go from these 10 million transits per night for 1 to 2 every night, depending on your filter, or hundreds or thousands. It depends how loose is your filter and what are you searching for. Now, how we communicate this is in 2 ways. So we have a real-time processing, real-time API, which basically within minutes from detection in Rubin, so we're talking, it's detected in Rubin, sent, processed by Fink, and actually communicated to, for example, your fellow facility. We're talking about minutes of difference. So this is pretty fast. It's great for fast transients like GRB afterglows, kilonova. And there is the other way, that is the science portal, which is basically a web page, and the API, which I'll show you at the end of this talk, that is basically the information that we accumulate every night. We put it in a web page publicly so you can access it. And this is a little bit more visual and easier to talk than a stream of candidates here. There is an interesting event. It's quite rich. Now, so we deployed with CTF since 2020. We have processed over 110 million of alerts, and we have different reduced streams to CTF data. So as an example here, I'm showing you a figure from our first paper. Here we take alerts between November 2019 and June 2020 with the first filters that we had. So these filters had some issues that we have fixed since then. On the bottom right, you can see all process alert from this month. So you can see the density is quite high. We have regions in the sky that have over 2,000 alerts, which is pretty large for basically 6 months of data. And then in the other panels, you can see some of the filter stream. So on the top left, I'm showing the solar system objects. So either known solar system objects or candidates. Then the orange and the green are actually transients that have a cross match either with a variable star, so they are probably a variable star, or are very close to a galaxy, so they have a probably they are extragalactic because they are close by to a galaxy. And then in red and in purple, I'm showing some of the candidates for supernova and microlensing events. Now, of course, this has evolved and we're becoming more and more proficient in doing this. And there's a lot of filters that we are creating as the community advances. So to give you an example, I'm going to show you a little bit what we have been doing with kilonova. So kilonova are basically, well, we only have had one from 2017. So a gravitational wave was detected from a neutron star merger. And then we follow it up around the world. You probably were part of these efforts. I was part when I was in Australia back then. And we tried to find if we could see an optical counterpart to that neutron star merger gravitational wave detection. And we found one. That's a kilonova. It's a fast evolving transient for us. I usually work with supernova, which lasts for months. Kilonova are not lasting that long. And with the collaboration called GRANDMA, which is a network of telescopes around the world, trying to find this kilonova, we created a filtering technique. So how does it work? We are right now processing the CTF stream. So that's around 1 million alerts per night. And what they wanted was to get some kilonova candidates out of that stream. So how do we do this? So basically what we did was we did our traditional cross-match. We're using CDS SIMBAT cross-match service. So basically you search for the coordinate, for example, here in the middle of the image, you can see an event. I'm going to try to draw this event here. And what we try to find is whether there is an object close by, like a known galaxy with this catalog, or maybe it's a variable star that is already cataloged, so that's not a kilonova candidate, or maybe you don't have anything in any catalog. So this could be something interesting. Of course, kilonova live in galaxies, so the first one will also be something interesting for them. So this is contextual information. So the people in GRANDMA also have access to a catalog called Mangrove, which is a catalog of local galaxies that could host a kilonova. So we cross-match it with that. Then what we did was, of course, we implemented a filtering where if LIGO Virgo is detecting gravitational waves and they send an alert, and here I'm showing to the right an image of some of the gravitational wave triggers they have had. So they would send a footprint and we basically will cross-match that footprint with all the transients that we have there within a time window, of course, not forever. And then for the classification, we have different things. We have, for example, the magnitude rates. So I'm showing here on the bottom right, a light curve on the top. So it's the apparent DC magnitude against observation date. This is CTF data for actually a kilonova candidate. And below in colors purple and red, you can find the delta magnitude as a function of time. And we can do this also normalized by days. So this is a quantitative thing that you can actually use to filter this stream. We also develop a machine learning kilonova score. So that's Biswajit Bigwas, which was a student with us that is preparing a paper on this kilonova machine learning algorithm. And with those values, we decided to do some customizable filtering to get the kilonova candidates for the GRANDMA collaboration. So what we did was basically output it in the different way that we can, real-time API, because what they wanted was to trigger their network of telescopes around the world to see if this was something interesting, but also through the science portal. And you can actually access that information right now from our science portal. So what they wanted was not a Kafka stream, which could be some of the alternatives that we have to actually communicate this reduced stream, but we created a Slack bot. Basically, they have a Slack channel that they receive the information from the possible kilonova candidates. And this is useful for them because actually kilonova candidates are not that much. So you receive 1 or 2 events maximum per day. So a Slack channel works pretty well. And that was the work of Juliette Vier, which she did the whole implementation for that bot. And we created different filterings. So there was one using the machine learning score, and there was one using only the catalog of the galaxy. So if a kilonova was in this galaxy. Then after all this happened, we talked a little bit more, and we wanted to try if we can use magnitude rates and slope to actually see if there was a kilonova that we missed from the other methods. So this is all part of an analysis that we are preparing right now with the GRAMMA collaboration in a paper using kilonova catcher citizen science. This is very interesting because not only GRAMMA is a telescope network like professional telescopes, but they also have an amateur astronomer program of citizen science where people can actually follow up interesting or promising kilonova events with their own telescopes and report it back. And they use those detections to do the kilonova search. So this is a very cool project that we deployed and still deployed in Fink. Of course, it's something that is evolving, and I hope the first results, you will see them soon online. Now, of course, Fink is much more than this. We are not only working with kilonova, we're also working with other science cases. So other ongoing projects that we're doing are here. Of course, this is not a complete list. As you may have seen, we had the microlensing filter from the start in Fink. This is something that's still available. I think microlensing is very interesting because you need a very long baseline to actually detect them. So it's very different from fast transients like GRB afterglows or kilonova that require just a very small amount of time. So for kilonova, I told you about the collaboration with GRAMMA. We also had sometimes in CFHT to follow up these kilonova events. We also have an ongoing project with GRB afterglows. So basically, there are different ways we can detect GRB afterglows. You can get Swift or Fermi detection, and you have a footprint of the possible object, the possible GRB source. And then you cross-match it and you try to find if there is something that we have detected that is within that footprint and do some filtering. So that's a way of detecting. But there is also another way, which is, well, let's say that the Swift and Fermi didn't detect anything or was not observing at the time. Can we find these afterglows without the GRB signal? So this is something that we are working with. And part of this work is also in preparation for SVOM. SVOM is a Chinese-French space mission, which is coming online pretty soon, which will be the next generation from Swift and Fermi. Now, once you think about kilonova and GRB afterglows, and we are getting all these images from the sky, you don't think too much that we also detect a lot of satellites, and even more than satellites, debris. So basically in space, there is a lot of material actually. You would say floating around, but it's not really floating around. It's still around the Earth, rotating around the Earth. They have very weird orbits, some of them, and they also rotate. So their luminosity changes with time, and it goes very fast. And Sergei Karpov is actually leading a project of using tracklets to actually find the orbits and track these satellites and debris. And that's a pretty cool paper that we didn't think we will have an application on that, and here we are. Of course, I am a supernova cosmologist, and a lot of the work that we are doing is around supernova. We have different models that we are working to identify supernova. There is an early supernova with active learning mechanisms that have been developed. This is to optimize training sets and optimize the follow-up, a spectroscopic follow-up of supernova candidates. So it's very early before the supernova really shines bright. This is led by Marco Leoni, and the paper is in preparation. It's very exciting because it's the first application of active learning to alert stream data. So this is something we're looking forward to. The results look pretty promising. And of course, I am also working with early and actually later supernova detection with recurrent neural networks. So I developed a framework that I published in 2020 called Supernova. This is a framework to classify regular time series efficiently. There's also Bayesian neural networks in it. But supernova is something that we're using in the dark energy survey as well to select our sample of supernova for cosmology. So we're trying to leverage that advancement in the dark energy survey also in Fink, so we can do cosmology and science using this framework. And the most exciting thing of all, maybe for some people, will be what we don't know. Rubin will produce such an amount of data that it's a needle in a haystack to find what is really, really, really weird. And part of the work that we're doing is anomaly detection. How do you find from those 10 million alerts every night, the handful that are promising anomalies? Of course, this is not a comprehensive list. There's much more that we can talk about. We want more collaborators. So if you have an idea of something to be done, we would love to hear from you. Just before I close up a little bit in my talk, we have ongoing collaborations with other telescopes and follow-up teams. I think it's important to see science right now as a community effort more than an isolated effort. So as I told you, we have partnerships with SVOM, GRAMMA, we have discussions with CTA, Integral, KM3Net, which are very different surveys to try to work with the data from everybody. Fink is actually integrated in different frameworks and softwares. For example, we have a transient name server bot. So we report every night automatically the promising supernova candidates to the community. They get a name. Most of the time they get follow-up. And until now, we have been very good. Like 90, I don't have the statistics right now, but it's 80 or 90% of the objects reported by Fink that are being spectroscopically follow-up end up being a supernova. So that's pretty good. Our levels of reporting are pretty good. We also have an integration with Las Cumbres Observatory Targets and Observation Manager. So basically, it's a way to trigger observations in Gemini, LCO, SOAR, using basically they have an interface which is very nice, and you can query some targets from, for example, Fink, and then send it to the telescope for observations. And most recently, we have integrated with Astro Colibri, which is a multi-wavelength, multi-messenger platform. And I'm showing below a little bit what it is. They basically show the recent GRBs, FRBs, weird bursts that they detect with multi-wavelength transients, multi-wavelength surveys. And there is a link now for Fink. I don't know if I can color here, but on the right panel, you have a link to Fink. So you can actually see the optical data from that object, if there is, or at least the alerts around this. So to end up, I'm gonna end up showing a little bit of how you can interact with Fink if you want to use it. So as I told you, we have 3 ways of communicating our data. There is a real-time API that can be a Kafka filter stream, a Slack bot. I won't show you that. The Slack bot is basically a message in the Slack. But I'm going to show you the Science Portal and the REST API. So how does the Science Portal work? And you're going to apologize. I'm going to apologize because the video I took it while the internet was super slow. So it's very slow reacting, but it's very good for explaining. So basically you go to finkportal.org, as you can see here, and you will see that we have a search bar. In that search bar, you can query by object ID, a cone search, a date search, a class search. So a class search, basically you click and you have all classes unknown, some of the candidates that we have already trimmed for you, but also things that are already classified, like TNS are spectroscopically confirmed things, or SIMBAT are the things that are cross-matched positionally, either to a variable star or transients that live in a galaxy, because sometimes you cannot resolve very well that. So here I'm searching for spectroscopically classified type 1a supernova. You can see you have the 100 closest alerts from that. And I'm clicking in one of them and you will see our science portal. This is the initial page. You will have the thumbnails from CTF, the light curve, some visualizations of the galaxy and the imaging around. You can change how the light curve appears. You can go to external links like TNS, SIMBAT catalog. You also have some features on the right. Then we have these profiles on the top. And in this case, this is a supernova. So it's useful to see the machine learning scores, the color magnitude evolution, color magnitude rate. Now, I'm going to show you the variable star one. This is a supernova, so forget this is not a great fit, but you can actually fit the periodicity under that data and see the I think they call it period folded data. And we have other profiles, we call them, for microlensing solar system, and the GRB profile is coming online pretty soon. We're working on that one. So this is the idea is that we can cater as many sciences as we can. For some sciences, it will be more adequate to see a period folded light curve. For others, it's just the color and magnitude rate. So feel free to take a look. We actually welcome feedback. So if there is something that will make your life easier, let us know. For example, we got some feedback from some people saying, no, we want is the rate of the color increasing per day. So we put that on the right. And all these features, you can actually use them when you query, even in this list here, you can actually go to the columns and actually put the command to filter the data. I want detection history to be less than 20, for example. So 20 points of observation. Sorry. So that's the science portal. Now in the science portal, you may see on the top left, there is something called API. So this is the REST API, the other way of accessing. This is like our documentation. You can actually curl to get data from our database in your computer. We usually use Python for analysis, so you can actually do that through Python. So we have created a set of tutorials that you can access from our webpage. It's all in GitHub, so you feel free to take a look around. And it's in Google Colab. So you can actually play with it online. So I'm gonna give you a show off of one of the tutorials that we have. This is the extragalactic science tutorial. So the idea is the following. We describe a little bit what you have, and what you need is basically to import requests and the packages you use for actually working with your data. Here we are querying for the AGNs in SIMBAT that have alerts recently, and we put a date range for that. And then you can get it in like a table, and you can do pandas data frame. It's a lot of fun. And then you can query, for example, for one of the objects, the photometry, and plot the light curve and play with it. You can also query for supernova candidates, kilonova candidates, things that are classified, not classified, etc. So it's pretty easy to use. We also welcome feedback if there is something that you would like, a feature that we don't have. One of the things that we recently did, and I didn't put it in the presentation, is that you can actually query Fink now through the, the address, like in the internet, instead of like making a physical query on the web page. This is a good way to link Fink to other web pages. So for example, if you're searching for alerts in a radius, this is a way to do it. Astro Colibri use it for this. So I hope I have convened that Rubin will be a big change for optical data. With 10 million transients per night, it's impossible that we actually look through all of them every day unless you have hundreds of thousands of students that want to watch and see them. I think we can do better. We can actually use these frameworks and these technologies to actually filter them out and find the science that you want to do. This is also a very reproducible way of doing science, in the sense, for example, selection functions, which in cosmology are a big thing, you can actually characterize them even 10 years after the survey. Especially because in Fink, we have a huge effort of versioning control. So basically you can see at this time which version of this machine learning algorithm, which version of this thing was used for actually selecting this object. So the power of Rubin is immense. We are a great asset for multi-messenger and multi-wavelength studies, especially with all these new facilities coming online like SKA. So how to unravel it? Basically, a broker. Fink is already designed for LSST, but it's also processing the CTF data, so you can try it right now. We have our first science modules deployed. We're already processing public BOE events and GCNs. We have this processing that is fast enough that within less than minutes, sometimes you can actually get a filter stream and deploy your follow-up survey. We have analysis capabilities with the web portal and API, which is Python callable, which I think is very nice because not everybody uses Postgres or things like that. And of course, the most important thing is that we want to connect to new team collaborations and facilities. So if in Brazil, you're interested in doing a type of science that we haven't talked here, or maybe something that we already talked here, but probably you have a big contribution to make. So we want to hear from you. And of course, now that I'm in Australia, I am trying to launch what I call AusFink, which is the Australian counterpart to Fink, in the sense that we're connected to the surveys and teams here in this side of the world, which is very interesting because if you think about it, when Chile, the sun is rising, the sun is setting in Australia, and sometimes you have night at the same time. So it's a perfect place to actually follow up very fast transients detected by Rubin. So it's a great place to go. So below you can see our web pages. Finkbroker.org is about our broker ecosystem. Fink portal is actually where you access the data. And of course, we have an email where you can write to us if you have questions, even after this talk. So with that, I close, and I'm very happy to take any questions you may have.
Thank you very much, Anais, for this remarkable, interesting talk. Now we have time for questions. If you joined us on YouTube, you can put your question in the comments section, and I will redirect it to Anais. So if you joined us on Zoom, please raise your hand and ask it yourself. Okay, go ahead, Julie.
Okay. Anais, thanks for this very impressive presentation.
Thank you.
You're welcome. I have, well, I think 2 questions perhaps. First of all, I suppose that I'm interested in solar system data. No, I am interested in solar system data. And for instance, rotational light curves and positions for the objects, But I do not intend to query or to use Fink every day. So for me, for instance, it would be more convenient to check the databases, your database each, I don't know, 15 days perhaps. How long will the alerts be stored in Fink?
We plan to store the 10 years of data and you can access the 10 years of data from Fink, the science portal, and the APA.
Okay, so
that won't be a problem.
okay, great. And another thing that is not clear to me is will it be easy, or is it possible to make an automatic link between, for instance, my computers or my programs to Fink? That is, instead of just entering data by hand, I can launch a program which will query data for selected objects and then get everything as automatically as possible.
Yeah, so there's two ways that you can do this. So let me go back to the slide to see if I can here. Okay. So there are two ways you can do this. So when we do the customizable filtering here on the top right, you can design a filter that is included in Fink, and you can access whatever you want. So basically you can query every 15 days through the science portal or the API. Look, I want all the candidates of solar system by the filter solar system. You put it a name, rotational, I don't know.
Okay.
Let's put it that way. So you can do that, and that will be available to everybody. The other way you can do it is through the science portal or the API, the curl that I showed you, or the Python script. You can query, I want all alerts that have this criteria. And you can actually do that. It doesn't need to be already predefined. You can actually go and say, look, I want all unknown candidates. From these unknown candidates, I want the ones that have only 2 detections and are this color, and you can get that. Now, that way, it's more like you can touch it more, but the issue is that it may be slower. Because, of course, when we process everything within the Fink ecosystem, because it's all distributed computing, is super fast. So within seconds, you will already have those candidates there, and it will be stored. So it depends on the science case you want to do, how much investment you want to do it. But both ways are good for us. If you're interested in doing a customizable filtering for your science case, just give us an email. We can start working on how to make it happen, actually. It should be pretty easy. We have integrated a bunch of filters already, and they are actually very scalable and I think easy to make. Okay,
great. And Rodrigo, if I have time for one more question.
Sure, go ahead.
Okay. Also, the LSST will discover a lot of new solar system objects. And well, I think that in the beginning, these objects will be perhaps unidentified as solar system objects. They'll be just a new discovery, but after some time, I think they'll have an orbit predefined, and it will receive a name. And when that happens, will previous observations in Fink be also updated? I mean, the first observations of a newly discovered object will be linked to the let's say to the definitive name of the new object, or this is something I have to do perhaps by myself?
This is a very interesting question, which is the first time I hear it, but you're spot on, actually. So I guess if we have the orbits, it can be done pretty easily to actually update that. For the time being, we haven't implemented something like that. But if you know how to, like, if you are actually an expert of this domain, and if it is something that it will be useful and it's easy to do, we can do it, actually. If it's not a big technical issue, and I don't think it, because once you have the orbit, it's pretty easy to cross-match. It should be completely possible. So this is a type of input that we would love to hear, because we are not solar system people, most of us. So that's why this is a community-driven effort. So feel free to come be part of a community and tell us these type of things, because I work with the things that happen in only one place.
Okay, thanks a lot, Anais.
Yeah, no worries. But yes, please let us know. We can work towards doing a more robust solar system studies. Definitely.
Sure. Thanks.
No worries.
Thank you,
Thanks,
Jim.
Rodrigo.
I have a question also. When you were explaining that, well, the similarities will be generated from different imaging data. So that means that only what survives the difference imaging that is going to be forwarded to Fink.
Yes.
Okay. So if I was interested in let's say single epoch position of stars, it's not going to be in the alerts. Only if it was something that is varying compared to the. Okay.
Yes. So it will have to go over a threshold. I cannot recall exactly what is the official threshold of LSST, but it will have to have over 3 sigma or 5 sigma detection threshold. So if it's a star that varies very little, you won't see it. If it suddenly meets a flare or it's a variable star, you will have it in Fink and you will have that information and the light curve and the position, etc. But if you're looking for very non-variable stars, then it's gonna be hard. Maybe by chance one day because the subtraction went wrong or something.
I think it will be part of the proprietary data for LSST.
Yes, of course. Yeah.
I have a quick question. Hi,
Okay,
Anais.
go ahead.
Well, fantastic presentation. You guys are really doing a great job. Just a quick question. I mean, so everything is going to be public. So you process all of this and then anybody can grab it. So is ISO participating at all in this? Because they have that a whole bunch of telescopes there. So what is their attitude, official attitude? Is there any? Because like you said, I mean, Australia can follow up and, complementing the observation. So I would imagine this would be somehow involved in the planning. Is there anything that you know, since you've been in France and now in Australia?
Well, it depends. So ISO is a big organization.
And I know, usually... I worked there for 10 years. So
yeah, it's a very big. It's a very big organization. Of course, there are groups that are putting requests for follow-up using ISO telescopes, but there is no official partnership that I know between LSST and ISO. So there is the Foremost project that you probably have heard of. So it will do a spectroscopic follow-up for LSST and has a bunch of Foremost. Yeah. Yes, because remember that Rubin is funded by NSF, which is the US. So although scientists were all from around the world, they have secure other projects to actually do follow-up. I haven't heard of a large-scale program in ISO, but I know science groups that will be interested in following up particular events. Yes.
Okay.
And I think that's the status quo right now. There's a lot of synergies happening right now and discussions with teams like Euclid or Nancy Roman and things like that.
Yeah.
But I haven't heard anything organized.
No, I haven't either. So, okay.
Yeah.
Well, great presentation. Fantastic work.
Thank you.
Congratulations.
Yeah, thank you. I hope you can use it for your science.
Yeah, well, I'm not sure we will use the time domain. It's not my cup of tea, but I can see the potential, enormous potential. Thank you very much. I'm going to have dinner now. You are waking up. I'm hungry.
Yes, I understand.
Anais, I have a question, another question concerning what you have available for the ZTF. What we have is, if I had a software or some routine that I wanted to test with Fink data for the future,
yes,
for what will come from LSST, can I test it already with what is available for ZTF?
Of course.
Okay, it's not going to change. It's
So Fink, the architecture, like the nutshell, is not going to change much. We have some plans on changing the database structure, but this is very internal. So there are two ways you can test your algorithm. One is querying and getting through the API, the data, and trying it up locally. But if you want to integrate it within Fink, we have a link in the finkbroker.org. So you can send us an email or go through there. There's a little form. If you have already an idea and a software, we can tell you exactly what you need to do to integrate it. For example, my machine learning classification algorithm, I did it for using tables, fits tables, for example. But I think we do everything on the fly. We don't save and create databases. So I created basically a wrapper to actually do it on the fly. So probably you would need to do something like that to make it integrate in Fink. We would have to sit down and discuss how to do it and what do you need to do and what we can do on our side to make it happen. But yeah, just drop us a line. It's pretty easy. We're pretty informal in that way, and we can start discussing. I cannot hear you anymore. I don't know if
Okay, sorry.
now, yes.
I had my microphone closed. Felipe, please go ahead.
Yes, thank you. Starting my camera. Okay, so I have two questions. First, thank you for the seminar. The first one is, you talked about the kind of integration with with alerts being reported or observed with Gemini, Solar, and this is I couldn't actually understand if this is something inside Fink, or I mean, you make a filter, and with this filter you start starting these observations, or is something apart from Fink?
So you're probably talking about the Las Cumbres Observatory's TOM.
Yeah.
So basically, they have a very nice interface where you can actually query, take targets from brokers. So for example, if you have already a filter target or an alert that you know already that's interesting, you can get all the information, the official RADEC, all the needed information for targeting the follow-up from Fink and the selection. So for example, you have a Kilonova candidate in Fink, you just click there, you search for a Kilonova candidate, and you send it there. Of course, this all depends if you have telescope time. They also have ways that you can get telescope time, etc. But it's already integrated in that way.
Oh, no, I see.
Is that what you mean?
Yeah. No, I understand you. So you can get the information from Fink, and it's integrated with TOM.
Yes, exactly.
Okay.
Now, yes, go for it.
You also mentioned, I think it's not linked to Fink, but you also mentioned some integration with amateur community. But yeah, so I wanted to know how this works.
So actually, this is the GRAMA collaboration that has this integration. So GRAMA is already a network of telescopes around the world. And they also have a citizen science project, or they call it citizen science, but it's like an amateur astronomer program. So what they do is, so we get the alerts from CTF, we filter them, we provide the possible triggers, and those triggers, they communicate it to amateur astronomers. And then they observe and they report back their observations to GRAMA. They don't report it back to Fink. Yeah, they don't report it back to Fink. The thing is that we cannot, like, there are so many science cases that when we go to Rubin, we cannot monitor all the reports by everybody. So it's right now what we are doing is that each collaboration that wants to create a citizen science program can do it independently and do it for their science. It's also a question about calibration. If you have ever worked with cosmology, you know that calibration between telescopes is not very straightforward. So putting everything in the same frame of magnitudes is not that clear. So it will be hard for us to actually integrate that right now. But this is something we're thinking and discussing with a lot of people as well.
Mm-hmm. Yeah, no, I'm a solar system.
Okay.
So no, very far from cosmology. But so talking about solar system, I surfed a little bit on the portal now, and I saw some information of solar system objects. So I understand that you don't have a specialist in solar systems, so we would need to create our filters to have proper, well, the magnitudes and the way we used to work and this. So we you don't have already someone working on these for the solar system. Is that right?
No, we actually, the only people that are working in solar system are the people searching for satellites in the RE. There are some, like you get some asteroids as well, but they move faster. So,
Okay.
So the difference in speed is so you have a mixture between the two of them. But of course, this is something that we don't have many people on. So if you're interested in developing a solar system specific thing, that would be great. We created actually a filter at one point because solar system objects, I'm sorry, but for when I do transient, sometimes there are my contaminants. So we try to identify them and take them out. So we created some solar system filter to try to get candidates of solar system objects. And there are different ways we have tried. One is color. So for example, if the color is red of the object, if you have two detections, or if it's just one detection and you find another one close by, things like that. But of course, we are not experts. So if you are keen, we will be more than happy to hear from you.
Okay. Well, thank you very much.
Yeah. So if you're a solar system person, actually, I didn't show this, but in the Fink portal, there is, I don't know if I can pop it up. My internet is not great when I'm doing Zoom. We have a sky map. So you can actually see all the objects detected in the solar system in a sky map. I think if you do it, see, no, sorry. I don't remember how to.
Yeah, you need to get the number of the objects, right?
Yeah, so you can do it this way. So this will show you the alerts. And then there is a sky map vision. Sorry, my internet is not great. You can actually see the span footprint. Yes, here it is. And then we are integrating the tracklets soon as well, so you can see like the orbit. But this is something that we're playing with. So if you're an expert, you probably know what you need more than what we're doing right now.
I see. Great, thank you.
No worries.
Thank you, Felipe. One last question. Okay, if there are no more questions, we will now wrap this up, and this presentation will be available on our website and on LIneA's YouTube channel. Just a little announcement for the next week's webinar. We will have Dragan Utter from the University of Chicago talking to us about universe probing with the Dark Energy Survey. Again, thank you everyone for attending, and a special thanks to Anais. Thank you very much.
Thank you for having me. It was very nice.
And everyone, have a great evening, and for Anais, a great day. Stay safe, and I hope to see you all again back next week. Thank you.
Thank you. Have a good night.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye. Have a good day.
Bye.